So 28. These problems are from the, they are from the Zumdahl textbook. This is the textbook that I prefer, but supposedly it's not as good for the AP exam, but I prefer Zumdahl over every other textbook. So, and this is page 581, which doesn't really matter, but just in case you have to go back, it's, you know, in the copy, so there we go. Okay. All right, so if you want, we can, we can go over them if you have questions, all right? So 28. And 29, let's start there. And did you get my little message about how if you're given an elementary step, that is going to be, you're going to use the coefficients as your exponents? Did you read that little message in the thing? Right, yeah, okay. So what that means is, okay, so what that means is, for example, if you're given here a proposed mechanism and you're given slow, fast, fast, you can assume that this is the mechanism with the coefficient as the exponent, because they've broken it down into the steps for you. So you can assume that this is an elementary step, that this is going to be, the mechanism is going to be the concentration of this to the 1. Because they broke it down into steps for you. You cannot take a full-blown equation and do that because there's so many steps embedded in it. But when they break it out for you like this, and you can cancel all your intermediaries and everything else, you can take the simple one, and then you can do it that way. All right, so we'll look at a few so you can see how that works. All right. Could you have done it? Well, no, because I calculated the K, and then they said, can you convert the K in, so this is actually the K using different numbers, using different units. Right. Okay, and then 31. So these are the answers that were in the back of the book. I don't know if you knew to check them, but in the back of the section, but and then 32. Sure. So in 31, yep. Yeah. So in 31, the first thing they wanted us to do was to find the rate law. So I went through and I said, okay, so here we're doubling, going up from 0.3 to 0.6. Oh, sorry. Let me go back here. Okay. So here it's staying the same, but here it's doubling, right? So going from here to here, it's doubling, and here it's staying the same. So I went from here to here, right? And I divided this by this. Turns out it's a 2, right? 2. So when I double the iodide, my rate doubles. So that makes this a 1. That's what that's for, right? That 1. I put a 1 here, okay? Next, I looked at this and I said, when I double, none of these stayed the same, so that made it kind of tough, right? Because I need to isolate this. But what I was able to find is that when I double this one here, and I double this one, so this goes up by 2, and this one goes up by 2, this goes up by 4. So that's 2 times 2 is 4, so that makes this one also a 1, because that verifies it, right? Because remember, you're going to multiply them together. So if I double this and this one doubles, then that also is a 1. So that means if I double this and double this, then this would be a 4. Does that make sense? Okay. So I doubled this and I doubled this, which would mean that if each one of these is a 1, this would go up by 4, and it did. Everybody okay? So that means that they're both 1s, which gives me a rate law here, where am I? Here, of them both having 1s. Next, it wanted me to calculate the value of the rate constant K. So you can pick any one of the samples and plug in. So that's what I did. I took the first one, 7.91. I plugged in each one of the concentrations, and then I solved for K. Now, because there were 2 variables, that meant that my concentrations were going to be molarity squared. So I subtracted 1 and then made it negative, which gave me molarity to the -1, S to the -1 for my units. Remember, you subtract 1 and make it negative. And that's going to give me my rate is going to be +1, because I'm going to have 1 left over and it's going to be positive. Okay? So then the next one was calculate the initial rate for the experiment where both iodide and hypochlorite are initially present at 0.15. So that's weird. Not what I did. I did not plug in at 0.15. Initially present. Calculate the initial rate.
I got a kind of similar answer. I ended up getting 8.2, or yeah, 8.2.
8.2?
Yeah.
Right, but you plugged in 0.15 here and right, so that's what I should have done. Right. So I just plugged in the wrong thing. So hang on. Right. I don't know why I did that. Oh, because I did that up here. I just plugged in the same number. So 0.15. So we plug in 0.15 here, 0.15 here, right? We just plug them in. Okay, and then you get 8.2 times 10 to the -2.
Yes.
Right, okay, there you go. Because one goes up and one goes down. Okay, there you go. Sorry. Okay. All right. What did I do? All right. So, does that help? Okay. And then 32 is exactly the same thing. The only difference is it ends up being 2 and 1. So that ends up being 3 minus 1 and then making it negative. So the units for the K are molarity to the -2, S to the -1. Okay? Questions? All right. Okay, number 41. Okay, second order, because the linear graph is 1 over the concentration of A. So that's a linear graph. That's the so that's a second order equation. All right. Now for number 42, what is the concentration of A after 9 seconds? So this took me a bit because I had to look up the equation and everything. But, so using the graphs, I estimated the starting concentration was at 0.05, and I did that from this graph. So I went to the initial concentration. Well, that wasn't really the initial concentration. I guess the initial concentration would have been higher. hard to estimate though, up here, right? You'd have to estimate. Hard to say where it would have been. What? Right, so this is the equation. This is the second order equation. So I used the second order equation, but I used 0.05 as the original amount, which probably I shouldn't have because that was actually at time 1. So you would have had to probably estimate, because we don't have any number at time 0. So you would have had to probably estimate at time 0. So it would have been up here, 0.05, 0.6, 0.7, so it would be like 0.08. So plugging in here, I just thought of that. 0.08 was my original amount. So this would have been 0.08, and then I would have solved. So my time, my half-life is 2.5. So here is my half-life. Half, and then half, and then half, and then half. So that's my half-life, right? Every 2.5 seconds. So 2.5 so I came down from 5 to 2.5 was 2.5 seconds. Oh, see, I started this at 0. That's what happened. I was thinking this was 0. So then I went to 2.5, but it's actually 2 seconds. From 0 to 3. So the half-life, does everybody, you see that? So I went from 0.5 to 2.5 here, 3 seconds. So from 1 to 3 seconds. That's a half-life. So my concentration is going from 0.05 to 0.025. That's half of it, and it's doing that in 2 seconds. Then it's going from 2.5 to basically like 1.25 in 2 seconds, right? So my half-life is about 2 seconds. So my half-life is 2 seconds, so that's wrong, just because my estimation is wrong, is 2 seconds. So then I'm going to come over here, and I'm going to say my half-life is 2 seconds. Okay, so let's just watch Miss Paxton do this problem. Okay, so my half-life is 2 seconds, because I just calculated that from the graph. So now my K is 0.693 divided by 2, right? So 3.465. Okay. So 0.3465 is my K. So now I have 0.08 is where I started. So 1 second, 7.5. This is going to be 0.7. So it's half of a half-life. Right. 5 to 10, 7.5. Okay. So I went from 1 second, so it's half of a half-life. So it's going to be about, it's actually probably about 0.8. That's probably about right. It's probably a good estimate. Okay. All right. So here we go. So now I'm ready to go. I'm going to change my K to 0.3465. And then what I did was I went through and pulled the formula. I went into my notes and I pulled the formula, because the second order formula, right? Because this is a second order. And then I just plugged everything in and I solved for T. So plugging everything in with t being 9, because the question is at 9 seconds, which is off the graph, what are we going to be at? Okay, so oh, it didn't work. So 6.4 times 10 to the minus 2. So that's the concentration at time t, at 9 seconds. Okay. So I solved for k and I did it all by graph. So am I right? Maybe. Am I off? Maybe, probably, right? I did it all by graph, by estimation. Okay. You can't. Because it's a logarithmic function. It's an exponential function, though. So take the half-life. Wait, can you just take the half-life of what it is at 0.5 and so you can in this case because there's no logarithm function here. But in the first order, if it's a first order, then you have to add in the logarithm, right? In this one, you could because this one actually is a second order. And there's no logarithm function here. So, okay, hang on. What are you asking? Yeah, so you remember that grid that I set up here? Do you remember the grid? So, okay, so starting at 1 second, so time at 1 second, 0 half-lives have passed, and there is, you're gonna say 0.05, right? And then you're gonna say at 3 seconds, 1 half-life has passed, and 0.025. But the problem is, so this all makes sense. At 5 seconds, 2 half-lives have passed, right? So this is fine. 7, 9, so 3, 4 half-lives, 0.025, 0.125, and then 625, right? But 9, so it's not right. I don't know, but I'm doing what you're saying, right? Right, because here we are at 6, and there's 0.0125 right here. So 0.5, and then at 1 half-life, which is 2 seconds, right? 0.25, right? And then 2 half-lives, which is 1 second. So that's 5, 0.125. But see, it slows down. I mean, I think it's because it's a logarithmic function, except I understand what you're saying, like, there is no logarithm in here, so because it's second order,
It is doing that though, isn't it?
slowing down, it
Well,
is.
no, I mean,
No, it is, because it's only going down by 0.6, it's going down by 0.3, and then it's going down by
right.
0.17, right? I don't have it. Right, because it's an even one. You know what, right?
Because you're saying if like at the beginning you're to like divide it, you would end up getting. Right, that's half of, yeah, yeah.
All right. Except that the linear one is 1 over. So then you're just gonna pull the flip it, like invert it? Okay. Mm. Let me look into this. I mean, whenever I do, I come back with it the next day, so, you know, because I don't want to take more time on this. So let's keep going. Okay, 53. All right, so in 53, this is a good example of what I was talking about elementary reactions. They're saying it's an elementary reaction, which means you can write the rate equation from the equation with the exponents.
Oh, that's what that means.
Right, using the coefficients as the exponents. So here are the elementary equations, and then here are the rate reactions, which of course you can't see both at the same time. So the rate here would be K times the concentration of this compound to the 1. Right, so you can use the coefficients as the exponents when when they tell you it's an elementary reaction, or when it's designated as the slow reaction and you've removed all of the catalysts and the intermediates. Because then it's now down to being just the elementary slow step. Okay? So for these 53, all I did was take the reactants and use the coefficient for them as the exponent. Sorry, there we go. Right, so here, like here's ozone plus nitrogen monoxide. So in B, right, ozone plus, so there it is. With no exponents because they both have coefficients of 1. If one of them had a coefficient of 2, then it would have an exponent of 2. In an elementary reaction, that's because they've broken it down to this is the slow step. And remember when we were talking about the problems with the fractions, and we were saying the rate is for the whole reaction, and so if the coefficient is 2, that means it's going to move over there twice as fast. Well, that's what that means. If I double the concentration, then the rate will go twice as fast, right? So when they give you an elementary reaction, this is how this reaction will react when the concentration of this compound is doubled. If you double the concentration, then the rate will double. Okay? So here is 53 with those rates. Now in 54, it's a little bit different. They gave you a mechanism, but they didn't identify the steps as being slow or fast. So the first thing I did was I took that mechanism and I put a box around all of the intermediaries. So here is the 2OH, and here's 1,2. This is an intermediary because it was produced as a product, and then it disappeared as reactants. So hydroxide, well, not hydroxide, OH is an intermediary. And then hydrogen with 2 oxygens attached is also an intermediary. Here it is produced, and then here it is used up. So these 2 compounds are intermediates. So they're not going to count in your reaction. So then the problem said, go to 33 and take a look at problem 33 and write your rate equation. So we didn't do 33, but I went to take a look at it. And when I went to take a look at it, what I saw was that assuming that the rate is equal to, and here's the rate, notice this equation that's given, it's not this. Which means that for every 1 hydrogen peroxide that goes over, that is the rate of the reaction, right? Which means that if I double the hydrogen peroxide, the rate is going to double, which means the exponent is 1. So that is this right here is going to be the rate, the rate determining step. So there it is. There's my rate step, step 1. Okay? So that's the only thing that's going to change my rate is the concentration of the hydrogen peroxide. The other thing, of course, is that that's the only thing that's there, is the hydrogen peroxide. Nothing else is even involved. It's a decomposition of hydrogen peroxide, right? So there's my step 1. If I double it, I double my rate. Okay? So my overall reaction, I added everything together, I subtracted out my intermediates, and there's my overall reaction. That's just like Hess's law. Remember adding everything together and subtracting everything out. But with regard to the rate, you're looking for the slow elementary step. You're going to subtract out your catalysts, you're going to subtract out your intermediates, and what's left, you're going to take a look and then look for evidence of if the rate changes. In that case, I looked and I saw that they had a rate step already with a 1/1. So that's going to indicate the base rate right there. The rate is equal to this. Okay? All right. Next, so the next one was pretty much the same. 55 was pretty much the same. They gave me another one. I canceled out my intermediates. I did the same thing. Here it is. I can put a box around my intermediates, made as a product, used up as a reactant. Made as a product, another one, used up as a reactant. So they are not included in my rate. I have 2 of these, right? And then that's all that I can cancel out or anything like that. So when I do my overall reaction, it's going to be this compound, these 2, yield my bromide, my butanol, and my H3O+. Okay? So there's my overall. All the things that I couldn't cancel out. Now, what about my rate? Well, there's only one thing left on my the one compound that's left other than the two waters. So I have a choice. I can, and that's in the slow step. So am I going to use the water in the fast step or the water in the fast step, or am I going to use the compound in the slow step? So the compound in the slow step, and it has no coefficient. So therefore, the coefficient of 1. So it's going to be the slow step as an elementary step. Okay? So there it is. Yes, I can. So there it is. My elementary step. There's the compound right here. The compound in my elementary step, right? With an exponent of 1. Because everything else got canceled out but the waters, and they're in my fast step. So that's not going to be it. It's going to be my slow step, right? Okay? Now, the next question was, what are the intermediates? Produced and then used up. So cancel, I put boxes around them, and there they are, the two intermediates. Okay? Number 56, the exact same question. I canceled out my intermediates, NO3, here it is and here it is, and I canceled out the catalyst, NO2, one of the NO2s and one of the NO2s canceled out. The other NO2, nitrogen dioxide, is still there. But one of the NO2 was used as a catalyst. So it shows up here as being put in as a reactant, and then it is comes out as a product. So therefore, so whether it's excess or it's a catalyst, it's hard to tell, but it's not used, right? So once I canceled them out, then I got an overall of nitrogen dioxide plus carbon monoxide yields nitrogen monoxide plus carbon dioxide. So that's my overall. And then what is my slow? I look at my slow. Here it is. So what's going to be my rate? My rate law is going to be rate equals K times this to the 1. All right? But look at how different that is compared to if I had used the rate from, to the 2? No, to the 1. Sorry, to the 1. To the 1, not to the 2. Because there's only one of them. See, there's only one here. So it's to the 1. Because in the slow step, there's only one. So not to the 2. All right? Once I cancel it out as being catalyst, it's done. So it's a lot different than if I had put it together and I had looked, I would have put each one of these in and said to the 1, right? So having it broken down into the elementary steps allows you to say, oh, well, once I break it down into the elementary steps, this is the only thing that's actually there, the nitrogen dioxide. The carbon monoxide isn't in the slow step. So that doesn't get included in the rate reaction. Okay? And the catalyst we don't include because, frankly, the catalyst isn't even in the ultimate equation. So that's why the catalyst isn't included. It's not in the overall equation at all. So it's not included in the rate reaction at all. Okay? Does that make sense? So you have to have, again, you have to have these elementary steps, be told it's an elementary step, or you have to have the slow and the fast steps so that you cancel out the intermediates, cancel out your catalysts. You have to know ultimately what is involved in these steps. And this is a good example. What does it boil down to being the actual overall reaction? Oh, there's only one nitrogen dioxide. In my slow step, there's 2 of them listed. But in the overall reaction, there's only one, and that's because one of them is a catalyst. So I'm not going to use that in my rate equation because it's a catalyst. All right? And then in 57, this was just a labeling of a graph. And I say just, but that absolutely could show up in one way, shape, or form. And if I was going to put in a catalyst, it would look like that.